All right, so last class led us into a new assignment, and judging by my emails, we have questions that we're going to talk about, which is cool. That's what we're here for. We're here to help everybody learn, and so sort of let's sort of transition into that stuff right now. And feel free, it's any point to speak up if you have any particular questions about the homework. Just to be clear, some of those problems that are on there, we haven't really showed you how to do yet. So if you're working ahead, that's fine, but do not stress about all that stuff just this moment. So what did we do that was sort of important? Last class, we stated the limit laws. And other theorems that help us analytically compute limits. So this is the operative phrase, analytically compute. One of the skills or one of the things that you must be able to do in this class in order to earn a passing grade, if you will, is you must be able to understand how one analytically computes a limit. That means symbolically with paper and pen or me on a whiteboard. You can investigate limits graphically. You can investigate limits using tables. You can verify your analytic work using graphing devices and tables. But the only way to logically 100% deduce the validity of a limit, you must use what we call these analytical tools. And we're going to ask you to do that this semester. And it's got to be something you can do. So let's jump basically right into some examples. And then we'll move on to some of the other things. So computing limits analytically can be thought of as a game. And the game is as follows. So let's start with something like this. The limit is x goes to -2 of 4x squared plus 6x minus 5. So I'm asked to compute a limit. Now, the game that I like to play is the following. I say to myself, can I plug -2 in to that expression? And the answer in this particular case is yes. I can just plug -2 in. And so to do that, I recognize that this is 4 times -2 squared plus 6 times -2 minus 5. And if you do your arithmetic, that's 16 minus 12 minus 5, which simplifies to -1. So this is what we call a very direct and easy calculation. Why is it direct and easy? Well, I'm taking the limit of a polynomial, and one of the limit laws in the theorems that we talked about on Tuesday says that for polynomials, you can just plug in the limiting value, or not the limiting value, but you could plug in the point of interest. We're interested in what's happening at -2. And so we can plug that number in. Now, that is not always the case. So if I look at another example, suppose I have the following. This time, let's look at the limit as x goes to 2 of, say, this creature. Now, if I try to play the same game, I run into a wall, because if I plug 2 in there, what happens is I end up dividing by 0, which we know is undefined, and we know makes 0 sense, pun intended. And so what we have to do is we have to rely on some other limit laws. And one of the limit laws we stated says that if you can do some symbolic algebra, if you can take the expression that we have and find an equivalent expression, then we're allowed to take the limit of that. So the key observation for this particular problem is to note that the numerator and the denominator both factor. Now, for many of us in a class like this, we're still not the quickest and at recognizing factorizations, but what you want to do is you want to work on that, because being able to factor is an essential skill to doing many of the things that we're going to do in this class. So, you know, with a little bit of trial and error, maybe you're good at factoring. What you'll recognize is that this factors into this. I hit the wrong button. Hold on a second. Wrote that wrong. Let me do it the other way. What you'll recognize is the numerator factors into x minus 2 times x minus 4. And these guys cancel out. And when they cancel out, because they're common factors, we're left with this expression. Now, even though I still have a fraction here, what you'll note is I can actually win the game now, because if I plug 2 in now, I don't get division by 0. So when I plug the number 2 in, what I end up getting is I get 2 minus 4 over 2 plus 2, which of course becomes negative 2 over 4, otherwise known as negative a half. Does anybody have a question about this? Comment. So again, I like to think of these types of problems, these computing limits, as a game. What's the game? It's as follows. Let me switch colors here. This is how I would encourage you to think about it. Plug 2 in for x if possible. If not, try algebra, whatever that means. And repeat. So that is how I learned to think about these problems. That will serve you well in most limits, not all of them, but most. And it's a good strategy to employ. Does anybody have a question about this? All right, let's look at another one. So one of the types we didn't consider yesterday was what happens when a factorization is not obvious. So let's look at something like the limit as x approaches 3 of the square root of x. Actually, not 3, let's say. Let's be more careful here. Sorry about that. So let's take the limit as x approaches 9 of the square root of x minus 3 over x minus 9. If we try to plug in 9, we get bad news. We can't plug in 9 here. So then we ask ourselves, okay, in the last example, we were able to recognize that we could cancel the bad factor out of the denominator. So if you go back to this example, and in the one we did on Tuesday as well, we recognize that there's a bad factor in the denominator. In this case, it's x minus 2. And so what we were doing in our game was we were trying to find it hidden in the numerator. And luckily, it was hidden up there. We found it. And so that's exciting. And when we found it up there, since there's a common factor to the numerator and the denominator, we are able to cancel them out, as we say. And that left us with an expression we could easily work with. In this particular problem, we recognize that the bad term, the bad guy, is the x minus 9. And the problem is we're not quite sure how to get rid of it. So what we're going to do is we're going to use a trick here, which is really not a trick. It's called a method. So I'm going to write it over here. So I'll put trick in quotations. What we're going to use is we're going to use what's called the conjugate. And you're going to say, what's the conjugate? The conjugate is something that you learned about in an algebra class. Although since the word conjugate's scary, you're probably like, I don't remember it. But basically, there's this following property that's very useful. If I take the square root of some letter A or some number A or some expression A, and I have minus B, and then if I multiply it by this expression that looks like it, but it's not. We call these expressions conjugates. You'll notice the only difference is one is a plus, the other is a minus. So that's called a conjugate. And if you multiply this out, what you'll notice is something very nice happens. Square root of A times square root of A is A, the square root squared. And then the middle terms, what you'll notice is these middle terms add up to 0. This and this equals 0. So at the end of the day, what you're ending up with is this simplifies to A minus B squared. So why is that useful? Well, what you'll notice, this trick, use the conjugate trick, is this eliminates the radical. So let's see how it might work. I'm not doing anything illegal because the way I'm going to employ the conjugate is I'm going to employ it in disguise. I'm going to write the number 1 in disguise. And you've been doing this since you were students in arithmetic class. The moment you learned how to find a common denominator, when you learned about fractions, was the first time you ever used this other trick called multiplying by 1. So I'm going to multiply by 1, only I'm not going to write 1. I'm going to write the conjugate divided by itself. So this is nothing more than a number 1. Now, because I've done this before, I understand that the hidden trick here, sort of the observation to make, is to multiply the numerator, but do not multiply the denominator. So what I mean by that is I am going to note that the numerator, when I multiply it, becomes x minus 9. And then the denominator I'm going to keep as is. So this is usually a step that we fail to appreciate when we first learn it. You'll notice that I multiplied the numerator together, but I did not multiply the factors in the denominator. And what's useful about what just happened is the square root is gone. And more importantly, that term x minus 9 that was causing me issues goes away. So since that goes away, the expression that I am left with is just 1 over the square root of x plus 3. Getting ahead of myself here. And now I'm able to play the game the way I want to play it, because I can plug in 9. Whoops. Without any repercussions. If I plug in 9 now, I'm not cheating, I'm not breaking the law. I am getting 1 over the square root of 9 plus 3, which of course simplifies to 1/6. Does anybody have a question? Comments? All right, so this is an important example. I hope that you will take the time to understand what it means. All right, so all right, we good? Any questions, comments? Going once, going twice. Okay, so if you look at problem 1 on homework 3, we have now given you the tools to compute all those limits correctly. Okay, so the next sort of obvious question might then be, what happens if algebra can't help us? So we have an example that we can sort of get on in pigtail off of. So you might remember our old friend. Limit as x goes to 0 of the sine of x over x. So we conjectured that this limit should be 1. And how did we conjecture this? We conjectured it using a table and the graph. But the question remains is, can we logically verify that that is indeed the limit? Does anybody have a question about this? Comments, concerns? So again, we want to know what the limit of this is. We think we know what it is. But how do we verify it? Well, it's worth pointing out the following, is that if I look at the expression sine of x over x, there's not much I can do algebraically. I can't factor the numerator. There's no obvious identities that I might use from trigonometry that will allow me to just plug 0 in. So what we're going to have to do is we're going to have to reason in a different way. So what I like to call this is, we're going to need some creative reasoning. So the first thing I want to do is draw a picture. And I'm going to do that as follows. Actually, let's make this. So what I'm going to do is I'm going to draw my XY axis. And then I'm going to draw some triangles, and I'm going to draw a circle. So let's do that. See if I can get this circle to work the way I want it. All right, that's my circle. It's close enough. Erase that, get out of there. I'm going to draw this line. Let me try to get my, and then I'm going to draw two other lines. So we'll draw this one. All right, so this is the picture I want to consider. I'm going to label some points here in a minute. So let's call this point A. Let's call this point B. We'll call this point C. Call this point D. And of course, let's call this O for origin. So what I'd like to do is I'd like to get an idea of what the sine of x over x might look like. And how I'm going to get an idea what that might look like is I'm going to draw some triangles, and I'm going to look at sines of x's, and I'm going to look at how I might be able to gain information about the expression sine of x over x. So the first thing I want you to understand is that this is so first off, the red circle is centered at the origin. With radius equal to 1. So that's an important observation for us to make. And now we're going to use, instead of using our calculus mind, let's travel back to being fifth graders, and let's just think purely visually. And when I say purely visually, here's what I want you to think about. What is the biggest shape that you see that I've drawn? Well, there's a few shapes, but what you notice is the following. So note triangle OBC is bigger than sector OAC which is bigger than triangle OAD. So think about that. I have a triangle that's inside a slice of pizza. So if you follow my pen, I have this triangle OAD, which sits inside of this slice of pie OAC, and that slice of pie sits inside of the triangle OBC. So if we write that in a little more sort of specific language, this means the area of triangle OAD must be less than the area of the sector, which must be less than the area of triangle OBC. Does anybody have a comment or a question? Now, if you're thinking, how would I have ever thought to do this? Well, no crap. No one was expecting you to do this on your own accord. That's why we have textbooks and videos on the internet. That's why we have classes, so that the information that is really difficult to discover on your own can be passed down from one person to the next. Luckily, someone figured this out a long time ago and was wise enough to put it in books so that new people can learn. And then they were putting it in other books and notes. And then we passed down this sort of strategy of learning. Okay, so now what we have to do is we have to say, what are these area formulas? We learned when we were children in school what the area of a triangle was. It's 1/2 the base times height. We learned in school what the area of a sector was. It's 1/2 the radius squared times the angle. So let's give this angle a name. Since the angle we were interested in the original problem was sine or x, we'll call this x. So what can we say about this creature? Well, let's go to the next page and let's draw it again. This time I'll do it a little quicker so we can see what's happening. So here's our circle. I'll make it bigger. So what colors did I use? Blue, purple, green, or blue, pink, green. So I'm just drawing this picture again for good measure. Because now we want to remember, this is the origin, this is x, this is A, B, C, D, and the length of this radius is 1. So for example, here's what we know. What is the sine of x? Well, the sine of x is equal to AD. I'll write it like this. That line, the opposite over the hypotenuse, which is 1. Remember, sine of x is opposite over the hypotenuse. So the opposite is the line AD, or segment AD, if you will. What else can we say? Similarly, we know that the cosine of x is what? Well, the cosine of x is OD over 1. And I'm getting this information. By the way, I'm trying to go slow, so if I'm boring you, I apologize, but I think this is an important exercise in problem solving. I get this information from the first triangle. Now I'm going to use the other triangle, the bigger one, and I'm going to say that the tangent of x, which is the opposite over adjacent, is BC over OC. But what's OC? OC is just 1, so that's equal to BC. Why is OC 1? Well, that's the radius of the circle. And so from these 3 facts, here's what I learned. I learned area of the triangle OAD. That's the smaller triangle. What is that? Well, it's 1/2 the base times the height. So it's 1/2, and then the base is cosine, that's OD, times the height, which is the sine. And then what's the area of the sector, which I'll call OAC? The area of that is, by definition, it's 1/2 times the radius squared. Well, the radius is 1. And then it's times the angle. What's the angle? The angle is x. And then lastly, what is the area of the triangle OBC? Well, by definition, that's 1/2 the base times the height. So that's 1/2 times the base, which is 1, times the height, which is BC. That's the tangent. And so we can put this all together. And we have a very, very important conclusion. We get that 1/2 cos of x times sine of x is less than x over 2, which is less than 1/2 the tangent of x. Okay, so let's not get lost at the big picture here. The big picture here is we're looking at a limit. So you might think, well, why? This has nothing to do with a limit. Well, it might not seem that way yet, but what I'm doing is I'm trying to gain information about the sine of x over x. And what I have now is I have two inequalities. And using this purple line that has two inequalities, I'm going to be able to get information about the sine of x over x. And not only am I getting information about it, but I'm getting information about it, and I'm going to relate it to two things I already have information on. So, I mean, that's really sort of like a microcosm of science. And it is a very useful theme of how we problem solve in science. If we have a new problem that we're not sure how to solve, what we can often do is reduce it or make it look like an old problem that we already have a solution for. So that's going to be my game plan here. My game plan is going to be to take this purple inequality, and I'm going to manipulate it. And once I manipulate it, I'm going to get information about the guy that I want information on. So let's see how that might work. So let's rearrange. If I start with what I had 1/2 cos x sine x. That is less than x over 2, and that was less than 1/2 tangent. But let's write tangent as sine over cosine. Now, don't forget, we're interested in the limit as x approaches 0. So we can assume that x is a small number, and we can also assume that it's positive. We can assume that x is between 0 and pi over 2. And then symmetry would give us the case if it was between 0 and negative pi over 2. So if I multiply this inequality by something positive, it doesn't change its validity. So I'm going to multiply everything by 2 over sine of x. If I multiply this by 2 over sine of x, what happens? Well, I get cosine of x. Which is x over the sine of x, which is less than 1 over the cosine of x. So let me reiterate what we did here. So why this was legal is we assume that x is between 0 and pi over 2, and multiply by 2 over sine. That kills the 1/2, and that also gives us what we want between x and sine of x. Or excuse me, between x and the sine of x. because now we can invert everything. If I flip everything, which is legal, when you flip everything, the inequalities reverse. So you obtain the cosine of x is less than sine of x over x, which is less than 1 over the cosine of x. So a similar argument shows this is true for negative pi over 2 less than x less than 0. Okay, so, and by the way, let me sort of interject. Most of the, we're not going to ask you to reproduce this argument. So don't stress about reproducing this argument. What you should do, though, is try to study this example, because this is a really good example in problem solving and how one strategy for how we might go about problem solving. We are interested in this sine of x over x. And so what we did is we went and drew a picture. And we logically deduced information about the sine of x over x. Now, what's useful about this equation in the pink is the guy I want information on, sine of x over x, is trapped between two expressions that I very well know how they behave. Does anybody have a question? All right, so where do we go from here? Any? Okay, so let's figure it out. So Since the cosine of x is less than sine of x over x is less than 1 over the cosine of x, it seems reasonable that the limit as x approaches 0 of the cosine should be less than or equal to the limit as x approaches 0 of the sine of x over x, which is less than or equal to the limit at x goes to 0 of 1 over the cosine of x. Now, what's nice about this is if you look at the two limits on the outside, we can do a direct substitution. Because if I do a direct substitution, I get the cosine of 0 must be less than or equal to this limit. And that must be less than or equal to 1 divided by the cosine of 0. But we know what the cosine of 0 is. The cosine of 0 is 1. And so what we've reasoned is that the limit we're after must be greater than or equal to 1, and at the same time less than or equal to the 1. And there's only one number on the planet that satisfies that. The only conclusion is that that limit is indeed 1, because that's the only value that would make that last line true. Does anybody have a question or a comment? So this was a very in-depth and tedious sort of problem. We spent a lot of time on. That's good. I encourage you to go back and try to make sense of this. And when I write, it seems reasonable that the following is true, you might say, well, is it actually? And the answer is yes. And the reason why this is true is because of what's called the squeeze theorem. What does the squeeze theorem say? Well, it says the following. Assume g of x is less than or equal to f of x is less than or equal to h of x on an interval containing a and we leave out the event that a might not be defined in one of those. Then these limits all have to abide by this inequality. So this is a completely different way of determining the value of a limit. Basically, what the squeeze theorem says is if you have one expression that's trapped between two others and you know how the top and the bottom guys behave, well, then we can trap the guy in the middle between the top and the bottom. And the important time when this limit or this theorem is useful is if the limit of g and the limit of h are the same thing. Then you can get definitive information about the limit of f. So let's look at a standard example how you might do this. Does anybody have a question, by the way? Comment? All right, so let's look at this guy. The limit of x squared times the sine of 1 over x. What does it equal? So if you make a table and or investigate the graph, it looks like the limit is 0. So perhaps you can go look at the graph, and we're going to do that in a second. We will use the squeeze theorem to verify this. So what I'm going to do is I'm going to pull up the graph in a second here. Bear with me a minute. So suppose you just go to Desmos. Oh, I guess I should share it with you. And if I graph this function sine of 1 over x times x, here's what the graph looks like. And you start zooming in and you're like, okay, this, can I get a sort of a gauge on the behavior? And when I put my cursor on the curve and I start moving it through, it looks like it's going to 0. And so I'm kind of convinced, but the question is, how do I show this? Okay, then if I look at the expression of the function, I might ask myself, I say, oh, I see that x squared there. Perhaps that square term is sort of using its power. You know, we see the oscillations, that's coming from the sine, but is there any characteristic of this graph that might be coming from the x squared term? So just out of the sake of curiosity, I'm going to graph y equals x squared. And when I do that, I notice something pretty cool. It looks to me like the red curve is trapped below the blue curve, which is y equals x squared. And then something even more challenges my mind. I recognize from my years in algebra that if I flip the x squared, I get this upside down parabola, which is green. And then I notice that this red curve is trapped below by the green curve, and it's trapped above by the blue curve. At least that's what the picture tells me. So through this little investigation, I think I have an idea of what's happening here. So that's exciting. The question is, how do I verify this? How do I verify in a logical way that what I see on Desmos is in fact correct? I can't just say, look at the picture, because we've already showed you that calculators can be misleading. Sometimes they make mistakes. Sometimes they don't show all the correct detail. But we are confident this is true, so we ask ourselves, can we verify it? And it's actually not too difficult to do that, provided we remember a basic fact about the trig functions. So let's recall the following. -1 is always less than or equal to the sine of x, and that's always less than or equal to 1. That is one of the basic facts of the trig functions. And this is true for any x. And so by that same reasoning, hold on one second. Oh boy. You allowed to have this?
Yeah.
You sure? Well, ask mommy to open it, please.
No, I can't.
You can't?
Yeah.
Okay. Hold on.
Daddy, open.
All right. Daddy's busy right now.
Oh.
Okay?
Okay.
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 Yeah, you're gonna. All right. Look, it's open now. Take it up to mommy. She'll finish it. Okay? Okay. All right. Go ask mommy to finish, please. Okay. All right. So anyhow, sorry about that. This is life in virtual learning.
Yeah.
All right. Hold on. We're gonna have to kick this kid out of here. Mute. Sorry about that. We have a sucker fiasco upstairs. All right. Now a kid's crying. So look here, what we have here is a basic fact of the sine. The sine is never bigger than 1. It's never less than -1. And that's true for any angle. So in particular, we can invert the angle, and the same is true for this. And this is true for any x not equal to 0. That's always going to be true. You could spend the rest of your life taking the sine of 1 over an angle, and it's always going to satisfy that inequality. And then what I can do now is I can multiply everything by x squared. That's legal because x squared is positive, so it's not going to change the validity of my inequalities. One of the things we learned in an algebra class is that if you have an inequality and you multiply both sides of it by a positive number, the inequality is valid still. And so what I've done here is I have done a similar thing than in our big example before, although that big example before took a long time to get here. Here we did it in 3 lines. Starting with a basic fact about sine, we were able to reason something about x squared times the sine of 1 over x. So what I did is I built inside, I built my middle function based on what limit I want to study. And so the squeeze theorem says I can take the limit of all three pieces. And when I take the limit of all three pieces, we get a very useful fact because the limit of the guy on the left and the right are both 0. And there's only one number on the planet that can at the same time be less than or equal to 0 and greater than or equal to 0. And the only number that satisfies that is 0 itself. And so, of course, what we can conclude is the limit is indeed 0, as we guessed. So that is how you use the squeeze theorem. Does anybody have a question or a comment about this? So if you look at your homework, problems 3 and 4 are very similar to this. In fact, problem 4 is almost identical to this argument. Does anybody have a comment, question? All right, so that's, again, an example of how you might use the squeeze theorem. I'm not going to pretend that it's easy to kind of understand the reasoning here. It takes some practice, and but you should read this as a logical sequence of events. I start with one fact, and I can deduce the next, deduce the next, deduce the next, etc. So we're doing a sequence of logical steps, and at the end we come down to there's only one logical conclusion. Okay, so let's move on. If we backtrack all the way to the beginning of class, we started by talking about computing limits. And we said that there's some theorems that essentially tell us all we have to do is plug the number in, and whatever we get, we get. And then in a situation where we plug in and we divide by 0, we can often help ourselves with some algebra, like we did on the earlier examples. Or sometimes we can do a more sophisticated line of reasoning using the squeeze theorem. But what happens if none of those options work? So that's kind of what we want to consider now. So does every limit exist? So for example, the limit as x goes to 0 of 1 over x. What does that equal? How about the limit as x goes to 0 of the absolute value of x over x? Does that exist? What about the limit as x goes to 2 of 5 plus x over x minus 2? What do these guys equal? You'll notice in each one of these three limits I plugged up, put on the screen, you can't plug the number in. So if we graph the functions, we might consider some new ideas. So what do I mean by that? Well, let's look at it. What's the graph of 1 over x look like? Well, the graph of 1 over x looks like this. So again, this is the graph. So what we notice is as x approaches 0 from the right, 1 over x gets large. And then similarly, as x approaches 0 from the left, 1 over x gets large and negative. It's kind of sloppy. So what this suggests is some new notation. It suggests some new ideas. For example, the smaller x gets, and you could even make a table to verify this, 1 over x keeps getting bigger, bigger, and bigger. And so what we do is we say, okay, the graph makes some suggestions of what we would say new notation. So the graph suggests maybe we adopt this kind of notation. So notice I'm using my English carefully. I'm saying the graph suggests this. We didn't define these yet, but if we're gonna use symbols to describe what the picture looks like, this looks very suggestive. The graph also suggests what else is happening. Suppose we don't want to think about what's happening near zero. Suppose we want to ask what's happening when x gets very big, when x gets large. So it also suggests writing this. As x goes larger and larger, as x grows without bound, as x goes to infinity, what happens to 1 over x? Well, it gets closer and closer to 0. These two ways of writing limits, this gives us, if we think sort of in the way we've been thinking about limits, if you think of this as far as input output, what this notation suggests, it says as the input keeps getting bigger and bigger and bigger, the output is getting closer and closer to 0. And that's precisely what we see when we look at the graph. So let's go back. We had 2 other examples. Let's look at these guys. So the next one we considered was this limit. The limit is x goes to 0 of the absolute value of x over x. So let's draw this. And maybe you're not too familiar with the absolute values. But this graph is actually very, very simple. It looks like the following. First off, it's undefined at 0. And so how would we illustrate that? We'd put an open dot here and an open dot here. But this is what the graph looks like. Pick any number for x, plug it in. This is height 1. This is height -1. That's what the graph looks like. And so this suggests, at least the graph, it suggests writing the limit as x approaches 0 from the left-hand side, which we'll put this little minus thing here. It suggests that this is equal to -1, and it suggests maybe this notation. Because when I approach 0 from the right-hand side, I'm always at height 1. When I approach from the left-hand side, I'm always at height -1. No matter what my input is, if it's positive, my output is 1. And if my input is negative, my output is -1. But notice, no matter what interval I choose around 0, I'm never going to have my output near the same number, because on one side of 0, all my output is 1. On the other side of 0, all my output is -1. And that directly contradicts the definition of a limit. Does anybody have a comment or a question? Comments, questions? All right, so I'm not going to waste too much time on this right now, but if we looked at, what was it, 5 plus x over x minus 2? Is that what it was? Yeah, 5 plus x over x minus 2. So lastly, the graph of y equals 5 plus x over x minus 2 suggests the following. It suggests that the limit as we approach 2 from the right is infinity. It suggests the limit as we approach 2 from the left is negative infinity. And it also suggests that the limit as x goes to infinity, as the input keeps getting bigger, the output gets getting closer and closer to 1. Now, you could go to Desmos to convince yourself, or you can reason it by drawing the graph anyhow, however you'd like to do it, but the graph's going to look like this. And by the way, you guys should have at one point in your lives in an algebra course sketch graphs of rational functions. The graph's going to look just like this. It's going to have an asymptote at x equals, so this is at 2. We'll define asymptotes soon enough. And then it's going to have a horizontal asymptote at 1. So what these 3 examples serve is they serve evidence that we need to sort of define some new things. So the 3 examples above suggest we need more what we can call types of limits. So what are these types? We need what are called one-sided limits. We should define infinite limits. And then lastly, limits at infinity. These are 3 things that we sort of need to examine more closely, or at least be aware of as options. So I'm not going to, sort of write down these definitions because they're very similar to what we wrote down for the definition of a limit, and you can easily read them if you need. So what does a one-sided limit look like? One-sided looks like this. We could approach A from the right. So that's the right-sided, or we can approach the limit from the left, or approach the value from the left is a more accurate way of saying it. We call this the left-sided limit, or left-handed limit. So the only difference you'll see here between our actual limit notation is you have these superscripts. The plus sign means we're coming from the right, and the minus sign tells us we're coming from the left. So the definition for these things is nothing more than the modified version. If you take the definition of an actual limit and modify it to only include values approaching from the right or the left. So here's an important theorem I'll state it as a fact. So now we know when a limit exists or doesn't exist. So the actual limit exists if and only if. The only way it can work is if the left-hand limit and the right-hand limit are equal. That's the only way the limit exists. So if we go back to, for example, this problem, this limit cannot exist because when I approach from one side, I get a different value than when I approach from the other side. In this example, the limit at 2 can't exist because I'm not even getting numerical values. I'm getting something that continues to grow. And so the symbol that we adopt and we use to show that something continues to grow without bound is the infinity symbol. Okay, so the next thing that we need to write down is what are called infinite limits. So we write limit as x approaches a from the right of f of x equals infinity if f of x grows without bound as x goes to a from the right. So essentially you can think of this as the closer your input gets to a from the right, the larger the output becomes. It keeps getting larger and larger and larger. Or you could think of it as you can make the output as large as you'd like by choosing the input sufficiently close to a, but to the right of it. Now, similarly, you can define this from the left-hand side and both can also use or have negative infinity. So we saw that with 2 of those examples. Comments, questions? So let's look at an example of how this might come to play. So let's take the limit as x approaches, let's say -2 from the left of 4x squared plus 7 over x squared minus 4. So I clearly can't plug in 2, because when I plug in 2, I get division by 0. Or excuse me, I can't plug in -2 either. And so the thing I ask myself is there any algebra? Well, the problem is the numerator won't factor. And since the numerator doesn't factor, that leads me to think that I might have an infinite limit. And so to verify it, what you have to do is you have to do the following. So let's note for x approximately -2, 4x squared plus 7 over x squared minus 4. What is this going to be? Well, the numerator is going to be approximately 23, but the denominator is going to be approximately 0. So let's look at it another way. If I look at the limit and I notice the denominator factors, even though the numerator doesn't, I can still make some observations. So let's ask ourselves again, we know what the numerator's becoming. This numerator approaches what? This approaches 23. But the denominator, what can we say about the denominator? Well, when x is approaching -2 from the left, that means it's a number. Think about what kind of number it's going to be. It's going to be, suppose, like if you're to the left of -2, you're like -2.1 or -2.01. And so that means that both terms are going to be negative numbers. You're going to have both factors in the denominator are going to be negative. And what's a negative times a negative? Well, a negative times a negative is a positive. So what we end up seeing is that the denominator is positive and approaches 0. So if we have 23 upstairs and downstairs we have positive numbers that are getting closer and closer to 0, what we expect is we expect it to be 1 over a very small positive number, which we expect to grow and grow and grow. So we illustrate that by writing infinity. Because that's a mistake, Heather. Yes, that should be a 2. Ha! That's not a 4, that's a 2. and one should be plus and the other should be minus. Nope, I just forgot what I was doing. All right, does this make sense though? These kinds of limits are sometimes tricky to reason. It takes some practice, and that's why we give you some practice with them. All right, so does anybody have a question? All right, so this is a good place for us to stop. And I would encourage you to continue working on this homework. Email me if you have specific questions. I'd be happy to answer them. One of the things that we'll ask you to do on the homework is, you know, we give special names when this sort of phenomenon happens. We say that a function has a vertical asymptote, and then when we have limits that be at infinity, we talk about what are called horizontal asymptotes. So we'll pick up on that discussion next time. Does anybody have a question, comment? All right, well then I say if you don't have any comments, I will talk to you after I sneeze. Excuse me. Ooh. I will talk to you guys next week. Someone said, is the homework due tomorrow? Heather, no, again, you could turn it in next week. That's fine. Yeah, if you're going to delay the homework to still work on it, that's cool. Please ask me questions though if you need help with any of it. And Heather, I know you emailed me. I don't remember if I don't think I responded. If I didn't answer anything today that you're curious about, send me an email and we'll help you out. All right, I will talk to you guys next week. And again, let me know if you need any questions answered. Take care.